supposed to be working? Are they supposed to be able to hear? Oh, yes, it does work. Okay, good. Good afternoon. As I told you last week, the most interesting system in the brain is the visual system. And we'll find out why today. And next week and the week after. Okay. So, first, two little questions. Sensory system. Is the eye like a camera? No. Is the eye like a camera? Yes, it is. Yes and no. Okay, so why yes and why no? Go ahead.
Yes, because of some of the various measurements, for example, it has a figure with a sort of aperture, light sensitivity.
Okay, so some of the parts, they've got a lens, it makes a focus, it's got a pupil, an inverted image. Okay, film. Well, what's our film in the eye? The photoreceptors. Okay, so that's yes. Good. Is the brain like a computer? What?
What sort of computer?
What sort of computer? This one. Yeah, this one. The one, that one, and that one. Is the brain like a computer? Go ahead.
Well, in some ways, yes. You're working with inputs and outputs and computation all those.
Inputs and outputs, memory, computation. Implementation is a little bit different. It's not silicon, it's biological. What else is different? Computation is parallel. Okay, exactly. So the brain is massively parallel computation. How many CPUs in the brain? Somewhere between 10 and 100 billion, because every neuron is a computer. Okay, so it's massively parallel. This computer is not massively parallel. It might have more than one CPU, but not many. Why not build a computer with many CPUs? Are there such things? Yes. MIT built what's called the connection machine using 1,000 computers like this, 1,000 CPUs. What's the problem? Energetically unfavorable. Okay, needs a lot of energy. That's very important to know, that the brain uses very little energy compared to a computer, and if we have 1,000 of them, it would use a lot of energy. Very good. Okay, what else?
A lot of programs are very difficult to parallelize. Doesn't resource have to say 460?
It's difficult to write the programs that they should work in parallel. When is it easy? When it's necessary to do many times the same thing. For example? Okay, crossing the threshold. But why do we need many of them? Why won't we have a crossing threshold detector 1? That would be nice to divide up, and every time we need to cross the thresholds, we'll have one come and ask that unit. Why do we need to cross the threshold many times? Many parallel inputs. Okay. For example? Many photoreceptors. Okay. So if we take the retina and we divide it up into pixels, then we can say that each pixel is doing exactly the same thing, the same processing, but on a different piece of the world. Okay? That's easy to program, because we just program the same thing in every piece of the retina. And we'll see that we can do the same thing when we get to V1. You've talked about V1 in Yuval and Weasel, so you know that every hypercolumn can do exactly the same thing, but just on a different input. That's easy to compute, and it was very easy for evolution to start out with an eye with a single photoreceptor, and then to repeat it and to build many. Okay? When is it difficult to do parallel processing? Give me a minute. When is it difficult? We just said when it's easy, so when is it difficult? When the variables are different. For example, if we want to have one piece of cortex for audition and one for vision, we might have to do different computations. Might. It'll be interesting to see when you're starting with vision, you're going to get to audition later in the course, to compare the two and to see if you can use the same basic computation for the two. Okay? And we'll see that in vision itself, there'll be different areas doing different types of computation. And usually we don't call this parallel computing, we call it distributed processing. Exactly. Okay? Good. So that's the brain-computer analogy. Now let's go to the eye. We said that the eye is somehow like and somehow not like a camera. Here's the comparison where it is like the pupil, the cornea, and so on. Okay? For those of you who speak Hebrew, why is the pupil called in Hebrew what? Ishon. What does Ishon mean? Ish katan. Why? A small man. Why is it called a small man? When you look at it, you see a small person. When I look at my lover's eyes, what do I see? Myself. Okay. Yes, that is one interpretation. It's probably the incorrect one. What other meaning is the word Ishon? I'm sorry for those who don't speak Hebrew. But it's important for you to know why pupil. Ishon Laila. Ishon means very dark. When we look into the pupil of someone else, we see black. Why do we see black? Because the light that's going in is being absorbed by the retina. Not correct.
Not by the retina, but
By the pigment after it. Yes and yet. Not correct. Did you ever go to a doctor and he looked into your eyes? Yeah. Why did he look into your eyes if all the light got absorbed? Why is it black when we look into an eye? Because we cover the light. Where is the source of light that's going into the eye and going to come out to us looking at it? Where does the source of light have to be? Right here. But our eye is there. So let's move our eye here. But if we move our eye here, then we're seeing this. Again, the source of the light has to be here. If the source of the light is here, it goes out here. So we have to put the source of light where our eye is. How can you do that? Shine a flashlight here, right? But how do you put a flashlight? If you put it between your eye and the other eye, then it's in the way. If you put it behind, then it doesn't get there either. So the trick is an ophthalmoscope, which is the source of light, a half-silvered mirror, which reflects half the light into that other person's eye, and then it comes out, and half of it goes this way, but half of it goes through, and this is where I put my eye. Got it? That's what an ophthalmoscope is. So I look through the half-silvered mirror, I can see into the eye where the light is shining into the eye. And then you see a very nice pink retina. Okay? Good. Just so we know what I'm talking about. Yeah. Sure.
Is the eye hollow?
Is the eye hollow? No, it's filled with a liquid. Yeah.
And how thick is what percentage of the volume of the eye is that liquid?
All of it.
All of it. So
It's totally filled. There's no air inside the eye.
no air, but is there a bulk of tissue?
There's no tissue here. There's a tissue. Yeah. The retina is a tissue.
So that's pretty thin. Is this to scale, right?
Pretty good. Retina is very thin. Yeah. Okay. Now, but that's important because how is light refracted? What refracts light? A moment of physics. What refracts light? Well, not reflect. Not reflect. Refract. I'm sorry. What is a lens? What is a lens? It's a piece of glass, yeah, which does what? Refracts light. Thank you. It changes the direction that the light goes so that light from this point goes straight through the lens, light also goes up to here and then gets bent down to go to the same point. That's how you get a focus. Is this obvious? Known? Yes? Okay. That's what refraction is. Now, why does glass refract light? Is there something special about glass? Exactly. So, what refracts the light? When do we get refraction? When you have an interface between different media, okay, with different indexes of refraction, okay? Where is the big change of media here? Air versus the cornea. So most of our refraction happens at the cornea. The lens does a very small correction. Okay? What happens when we're swimming? When we have water cornea? We get less refraction. Okay? So we don't get a good image. Okay? What about animals that spend their lives in water, like fish? How come they're able to see? Yeah, but their cornea is still much closer to water than it is to air. And therefore, their corneas do not bend light as well as ours do. So they need a much stronger lens. And their lens is much more round than flat. Okay? So on Friday night, when you're eating carp, take the eye and have a look at it. Now, if it's been cooked, it'll be solid white. It won't be transparent. Okay? If you can take it out before it's cooked, that's better. But at least after it's cooked, look at it and see that it's round like a marble. Okay. There's another funny thing about our eye, and that is that the retina is inside out. Where are the photoreceptors of our retina? They're on the back edge, not on the front edge. Now that's crazy, right? Why is it crazy? For two reasons it's crazy. Because light comes from the front. Why have the light go through all this tissue before it hits the photoreceptors? There's another reason why it's crazy. It gets distorted because it's going through the other cells. That's what we said. But there's another reason why it's crazy. No, another reason. Yeah. Exactly. You want the information to go to the back of the eye because ultimately it has to go out of the eye to go to the brain. So what does this cause? A hole in the retina. Because the ganglion cells, which send their fibers to the brain, are on the front end. They have to somehow get through. And they all go through this one spot, the optic nerve. And that causes a blind spot. Okay? You've got a demonstration in the book of the blind spot. Do it in the book. It's impossible to get the right distances for everybody here. Okay, good. So these are the ways the eye is like a camera. Why is it different? I'm sorry, you're right. Thank you. Yes, what's the advantage? Yes. In other words, the engineer who designed the eye was not crazy. There were two defects, but there must have been an advantage to make it worthwhile. So what's the advantage? Yes. It is always possible to say it's a flaw. But what would be the advantage in any case? Okay. So the first question is, why don't I see out of the back of my head? Well, my hair sort of bothers the light from coming through. But if I shave my hair, then the light should go through. Light goes through skin pretty well. It even goes through bone pretty well. Why should the light come through and go to the photoreceptors.
Because of a blind spot.
No. Because it's pigment behind the retina. Behind the retina, there's a pigment epithelium. There's like a skin of 6 pigments which blocks the light coming from the side. Okay? All eyes have to have that if you want to know the direction where light is coming from. Okay? It's one of the first design elements of an eye is to have something to block the light from coming from the wrong direction. Okay? Now, that pigment epithelium also is the source of energy to the retina. The majority of the blood vessels which are coming to give oxygen to the retina, and the retina needs a lot of oxygen, comes from the pigment epithelium. And most of that energy is used by the photoreceptors. Therefore, the photoreceptors are placed next to the pigment epithelium. Okay? That's the advantage. Okay, let's define vision. We're finally ready. We know what an eye is. We're not so sure what the purpose of taking the picture is. Let's define vision. Okay?
So Dan is shy, wants to ask a question.
Go ahead, ask the question.
So people, albino people, they do not have the pigment, the black pigment, right? So
That's
they
a
can
very good
see.
question. They don't have pigment in the iris.
Right.
Do they not have the pigment epithelium which absorbs it? I don't know, to tell you the truth. Okay. Let's say they don't have it. Therefore, they would see much fuzzier pictures and see also a scattered light coming from around.
The light goes back, right? Not just go to the eye, it can go.
Okay, the going back is something else. Okay. You know that you're driving sometimes on the highway and a dog comes and looks at you and you see the bright eyes. Because they, instead of having a pigment epithelium to absorb the light, they have a mirror which reflects the light back. What's the advantage and disadvantage? Advantage, they get twice as much chance of absorbing the light because it goes both ways. Disadvantage is some scatter and therefore the image is okay. But I don't think that albino have that. Okay. Okay. Define vision. What is vision? Come on. Everybody can say what is vision. Go ahead. What is vision? You have vision. What do you have? What is vision? Something. Say something about it.
Information about count, physical.
Okay. Vision is a way we can count physical stimuli. Go ahead.
How we understand what's around us, physical.
Vision is a way of understanding what's happening in the world. Correct. Yeah.
Extracting information from electromagnetic waves.
Extracting it. Okay. Very good. Now let's put all those 3 together, and we'll get to my definition. So here's my definition. Vision is building an internal representation of the external world on the basis of optical signals, electromagnetic signals. A representation that enables or facilitates responding to changes in the external world. Okay. So, yes. First of all, vision is not taking a picture. If our eye was a camera which took a picture of the world and sent that picture to the brain, we would need in the brain another camera to look at that picture. Cameras only help us make pictures so that we can look at them, but then we have to look at them. So taking a picture is the wrong idea of what it is. Vision is building an internal representation. But what kind of representation? You've already heard about Hugel and Weigel, and you know that the internal representation of the vision ultimately is in terms of people and objects and categories and so on. Which is a more exact representation of the world? The far high level interpretation in terms of objects, or the interpretation on the retina? Which is more exact? The retina. So why do we need the next one? If the retina has the more exact representation, why aren't we satisfied with that? Because it's not relevant. What does relevant mean? It facilitates responding to the world. We want to be able to respond. If you tell me that there's a blue dot here, and 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 white ones in between, I don't know anything. But if you tell me there's a letter W, then I know something. So I need a representation in terms of how I'm going to respond. Okay. The signals, yes, they have to be optical signals. Otherwise, it would be audition. Okay. And why did I say changes in the external world? Because we look at movement. Yeah. Movement is changes. And movement is important. Changes are important. I don't have to look at the world in order to know what was there 5 minutes ago. I already know. I looked 5 minutes ago. I only have to know what changed. Everything else is in memory. Well, not really. But essentially, okay, we really know already what's there. We only have to look at changes. Okay? Therefore, we're going to build a representation which emphasizes changes. We'll talk about that the second hour. Okay. How do we acquire signals? Well, from specialized nerve cells. Here's another question for you all. You learned already everything about the nervous system? What is the one trick that the nervous system knows? And I'm claiming that it knows only one trick. Well, it's a two-part trick. But what is that two-part trick that the nervous system uses for all signals? All signals in the brain, all signals in the nervous system depend on this one mechanism. Changing metabolic energy to electrical energy, yeah. Go ahead. Dimensionality reduction. Yeah. I want to get really at the essentials. What? Increasing signals. Yeah. But how does it create a signal? How does the nervous system create a signal? How does a nerve cell create a signal? That's what I'm trying to get at. Action potential. Well, action potential is one example of one of the signals. Now, how do you create an action potential? That's what I'm trying to get at. How do you create an action potential? Ion channels is a very good point. Yes, we have to have different ion channels. Now, what about them? How do we use different ion channels to make a signal? We have specific physical channels, and we use specific physical signals to do what? Yes, we want to use the signal to do something with the channels. What do we do with the channels? We open and close them. Okay, good, we're getting there. So now what we're saying is we open and close channels. Okay? Why does opening and closing a channel make a difference? It changes the membrane potential. Why does it change the membrane potential? Because? Ion flux. Why do the ions flux? Why do they move? Because you change the conductions. You change the conductions, then it flows. But why does it flow? What makes it flow? There's a potential. What creates the potential? Electrochemical gradient. What creates the electrochemical gradient? Pumps. What do the pumps do? Okay, so we have selective pumps. This is the two parts. The first part is we have selective pumps which make concentration gradients in the cell. Generally, what is the concentration gradient? In which direction are the pumps generally? What goes out and what comes in? Sodium goes out, potassium goes in. Okay. Now, after we have a concentration gradient, we have an electromagnetic force. Why do we have a force? Because where are we at rest, generally? Near which potential, the potassium or the sodium? Near the potassium. Why? Because in greater conduction. There's more conduction for the potassium than there is for the sodium. Now comes a signal. And what does the signal do? It selectively changes the conductance of the channels. In this case, generally what? Opening sodium channels. Okay? So, let's divide between the generally and the specific. The general thing is that we have pumps which create a concentration gradient. And number two, we have a signal which selectively changes the conductance of certain ions. Okay? That's the only trick that the brain knows. Now we're going to see how that works. You know already how that works for sensors? Did you talk about any sensors, Ivy? No. Okay, so that's transduction. Transduction is to do the same thing with a sensor. Just two examples before we go. How does it work with an action potential? What's the signal? What's the signal that creates the action potential? What receives the signal? Yes, but now we've got an action potential. What makes the action potential go along the axon? The channels and the myelin. But what makes the signal? The voltage. There's a voltage signal. So the signal is voltage. And what does the voltage do? It opens channels. And opening the channels makes more voltage, which makes more channels. I'm not supposed to be teaching that. Okay. Good. So that's the trick. The nervous system knows in what to use a pump to build a concentration gradient, change the conductance of specific ion. There are important principles. First of all, the energy that is used is metabolic. It's stored previous to the time of use. The incoming signal is only a trigger to use the metabolic energy. Okay? The voltage in the action potential isn't used to open the channels. Yes, it is. But then, once the channels are open, what's coming in are the flow of ions. And most of the energy is the flow of ions. Where did it get that energy? By creating the concentration gradient. The same thing is with vision. The light energy is not used to create a signal. It's only to trigger the signal. Very little energy in the light causes a huge signal. Okay. The sensing molecule and the specific conductance channel may be separate or they may be together. Okay. In the action potential, it's the gate itself which senses the voltage and which opens and closes. In vision, they're separate. And that's what we're going to get to. Okay. In vision, you can have a depolarizing or a hyperpolarizing signal. And different animals use different signals. Generally, invertebrates use a depolarizing signal. Vertebrates generally use a hyperpolarizing signal. Okay. When you have a depolarizing signal, after the cell is depolarized, you can have your normal action potential unit, which sees the depolarization and causes spikes. Okay? If you have a hyperpolarizing signal, you can't do that. Hyperpolarization never causes spikes. Okay? We call this signal a receptor potential. And when it creates spikes, we call it a generator potential because it generates the spike. Okay? In both cases, this is graded with the intensity of light. The more light, the greater the signal. The more light, the greater the signal. The greater the signal, what happens to the spike? The greater the signal, the higher the frequency of spikes. Frequency, not amplitude. Okay? So there are two essential types of signals in the brain, the graded potentials and the all or none potentials. One more example of a graded potential, please, that you've learned about already. The synaptic potential. Okay. They're both receptor potentials. This one is also a generator potential. It could happen in some cases, it happens in a separate cell. The generator potential, the receptor potential causes in another cell via synapse a generator potential which happens. Okay. How does that happen? That we get a hyperpolarizing signal. That's contrary to everything you've learned about action potential. Okay? So the answer is that in the dark, the sodium channels are open, not closed. Since they're open, we have a sodium electromotive force, which is like a depolarization. So the cell is basically depolarized in the dark. When the light is turned on, we close the sodium channel, and therefore we go back to a potassium electromotive force. Okay? So it's in reverse, but the same principle. Got it? Why is it useful that in the dark we're depolarized and in the light we're hyperpolarized? Which one is using more energy? In the dark there's more energy. We have all this flow and the pump has to work very hard. In the light, that's closed, so once we get to equilibrium, we're okay. Okay? But we spend most of our lives in the light, so we want to use less energy in the light. Or we want to use, when we're in the light and we're looking and we're doing, we want to save energy. When we're asleep, we don't mind using it. Okay. Rods and cones. Okay, let's say a word about rods and cones very quickly. Here's first of all a picture. The rods have very long outer segments. The cones are very short outer segments. You guys know about rods and cones or nothing at all? Yeah, sure you do. Everything. Okay, good. Both cells have a cell body. Both cells have an ending which has a synapse to the bipolar cells. One of the essential differences is that here they're infolding with a lot of rhodopsin. Here those infoldings have been closed off by an external membrane, and therefore they're like this within. These are much bigger, longer, the rods, therefore they have a lot more rhodopsin. Therefore they have much better chance of absorbing light. Go ahead.
But there is no light, not a lot of light in the roads.
There's not a lot of light. That's why you want a better chance to absorb light. Exactly. Here where there's a lot of light, you don't mind. Exactly. So we have sensitivity versus acuity. I understand the difference in sensitivity. The rods are very long and therefore they're more sensitive. Why is the acuity better for the cones? Because light coming from the wrong angle will hit these anyway because it's very long. While here, if it's coming from the right angle, it's going to miss it. So therefore, this has a better chance of absorbing, not only because it's longer, but because coming from the wrong direction a little bit will also be absorbed. Lots of rhodopsin versus less rhodopsin, one type versus three types. There are three types of cones. We'll talk about color vision later. Located mainly in the central versus mainly in the periphery of the retina. If you want to look at a very dim star, don't look at it because you have very few rods there. Look next to it where you have more rods. And finally, night versus day vision. Okay, we shall continue with that. Let's go quickly over absorption of light and what it does. So we already said that light activates the rhodopsin, which is in the discs or in the infolding. I'm sorry, these are both rods in the dark and in the light. Okay, in the dark the channels are open, and in the light they're closed. What happens is that rhodopsin, and this is a picture of rhodopsin. Inside rhodopsin, part of this huge molecule is this thing, which is retinine or vitamin A. So eat your carrots. And this changes its shape when it absorbs light. And it's this which is the right size to absorb light. Okay. If this were a different size, it would miss the light. If it was too small, light would pass by. If it was too big, okay. It has to be the size of the wavelength of light. So why do we absorb different colored light differently? Because we get close to the right energy, the right size with different amounts. And what exactly is the shape of this is dependent on the opsin as well. So changes in the opsin change from one cone to another and to absorb light of different colors. Okay, what happens? We start out with this bent form of the rhodopsin, of the retinine, and then light very, very quickly straightens it out, and then it goes through a cascade of changes, metarodopsin 1, metarodopsin 2, which is the active form, but that also then breaks up into the opsin and all-trans retinal, and then in a few minutes we can reconstruct it in the pigment epithelium probably. Okay. A little bit more details, just so that you should know. The important thing here is that the channel for the sodium has nothing to do with the rhodopsin. They're separate. And there's a G protein in between. Okay. So light changes the rhodopsin. The rhodopsin goes to the metarodopsin 2 form. That interacts with the G protein, which interacts with the GTP going to cyclic GMP, which reduces the amount of this happening. So therefore, there's more cyclic GMP in the dark, less in the light, and it's the cyclic GMP which opens the channels. This is milliseconds, because it's a process which takes time to diffuse. Actually, the metarodopsin 2 diffuses in the membrane until it gets to the transducer. And it can hit about 1,000 transducent molecules. Okay. And then the transducer molecules will interact with the phosphodiesterase there, which, again, then there's a multiplication of about 1,000. So we have lots of multiplication, amplification factors going between the number of rhodopsins which are hit by photons and the final response.
So it takes milliseconds to respond and then also milliseconds to close?
Yes, exactly. Now the closing I wanted to talk about, because the closing is not done only passively, but also actively. Okay, this was just once again the same picture, with rhodopsin becoming metarodopsin 2, interacting with the transducin, the G protein, which in this form of transducin GTP, it splits up into an alpha subunit, which then affects the phosphodiesterase, which activates the cyclic GMP hydrolysis, okay, which stops the opening of the channels. Okay, and when this is actually changing the concentration of cyclic GMP in the bath and recording from a piece of photoreceptor, and you can see in the light that it's noisy and that you can open up channels and so on. Okay. Or you can absorb a rod into a pipette and then shine light on it. And you can record the signal, and again you get a signal which is noisy and with photon response. Okay. Now, the ending of the response happens in a number of ways. One is that the metarhodopsin 2 gets reabsorbed back into, it becomes inactivated. It goes to further forms and the breaking up of the rhodopsin. Okay. There's also that its effects are broken up by its effect on the transducin is interrupted by, is activated by calcium. And when these channels close, they close also the introduction of a calcium. The calcium concentration goes down, and you lower that effect. So light stops the calcium entrance, which lowers the concentration, and therefore you accelerate the, you de-accelerate the interaction between metarhodopsin and transducin. Okay? So there are a number of ways in which calcium reduction speeds up the end of the signal. And I want to tell you something about how this happens. That light activation does two things. First of all, it activates, and second of all, at the same time, it begins its decrease of activation. Okay? And that's why we get responses which are transient in nature. All responses are transient. They start with a transient response and then continue with a steady state response, which is less. And what I'd like to do now is to tell you about that. If I can get the lights on. How can I get it on? Got it. Okay. So, I want to draw a graph. Can I do this yet? I want to draw a graph of the response versus the intensity of light. Okay? And I'm going to draw first the steady state response. You don't have to copy this because the next slide is going to show it again. But I want to do it with you rather than show you the result. Okay? So, the response at steady state against intensity is nonlinear and constantly increasing, but increasing at a lower and lower rate. So that we are less sensitive to high intensity than to slow intensity. Okay? That's the steady state response. That's when we give a light of this intensity. Let's call it here, I0. We wait a long time, we get this response. Steady state. Okay? This, let's talk about the amount of hyperpolarization that we get. Okay? But the same is going to be true for the spike rate in the brain. Okay? We can talk about the spike rate in the brain, same thing. So what I'm trying to claim is that overall in the visual system, this is what you're going to find. Okay? Now, what happens when we increase the light from I0 to 2 times I0? We get a transient which reduces to a steady state. Now we know what the steady state is. We've already drawn it. This is the steady state. This is the response to 2 times I0, steady state. And this I should have written here, I0. Okay? But that's not what happens. What happens, the transient, is linear with the amount of light. We double the amount of light, we double the response. This response, the response of the transient to 2 times I0, is just equal to 2 times the response to I0. Okay? Then, if we wait a while, we get a change of the response to the steady state, from the transient to the steady state. What is this process called? Light adaptation. We're adapting to the light. Okay? Yeah? Yes, to the steady state. It's 2 times the response to the steady state. Now, let's reduce the light back from this steady state back to I0. We again take a straight line and we go down to here. This is half of that. Okay? So the response to the transient at I0, which I0? When I come from 2 times I0 and I go to I0. And that's equal to 1/2 of the response at the steady state to 2 times I0. Clear? Now we wait some time and the response increases. What's that called? Dark adaptation, exactly. So the response to I0 to 2 times I0 and down, the response is going to be a transient, a steady state, a transient, a steady state. I didn't put a 0 because I don't know where to make it look accurate. Okay. But the idea is that this is double, so I really have to make this the 0, and then this is half of that, so I exaggerated. Okay. Better? Is this clear? That's the difference between transient and steady state. I'm afraid this is not in the book because I made it up. Whether it's true or not doesn't matter. You have to listen to me because I write the exam. Okay, so here it is. We start here, 10 units, 20 units, I0, 2 times I0. We go up to double and we go down to half. Yes, go ahead.
Isn't the time between light adaptation and adaptation longer for dark?
Yes, it is. We really have to talk about the mechanisms of light adaptation, dark adaptation. Okay, so we mentioned some of the processes of dark adaptation, the calcium coming in and so on. There's also a depletion of the rhodopsin. You can deplete the rhodopsin. That means hit it with light and break it up very quickly. But to reconstitute it takes a long time, like half an hour. So you go into a movie theater when the movie's already on and it's dark and you can't see anything. And you look around, where's your friend? You can't find him and so on. The movie's almost over and you look around, you can see everybody in the hall. Dark adaptation, it takes about half an hour. You go out of the movie theater into the bright sun, it's dazzling and hurting at first, but in a few minutes it's over. Okay, so it's much faster. One more thing, sensitivity. What is the definition of sensitivity? The definition of sensitivity is the change in response per unit light, per unit signal. Okay? Where are we more sensitive, in the light or in the dark? Now there are 2 measures, but let's take first of all the transient one. This green line is the one when we're light adaptive. This red line is when we're dark adaptive. Which one is more sensitive? Well, just the slope. We're more sensitive in the dark than we are to the light. So this change of slope is a change of sensitivity. Okay. There's another measure of sensitivity, which is the steady state sensitivity. And that is the slope here versus the slope here. And once again, this slope is slightly greater than this slope. Okay. I drew this for convenience as a square root. It's usually drawn as a log. Doesn't matter. As long as it's a continuous function which has constantly increasing, but constantly increasing at a slower rate. Are we supposed to do a haftakah? Haftakah 5 dakot, 5-minute break, and then let's go on. Sha'al, ask. Sha'al,
This,
whatever you want. מה שאתה רוצה. צרפתי?
לא הבנתי ממש את
כן, מה?
מה המכניזם שעושה את ההחמרה ואיפה האודופסין נמצא.
Alright, והקון, בתוך
הוא נמצא בממברנה
בממברנה.
של הפוטורספטור.
כן.
רציתי אבל זה נראה כמו ממברנה של התא.
זה ממברנה חיצונית וזה הממברנה של הדיסק. You see, I told you that there were these little discs. These discs have membranes. זה קון וזה רod, הם פוטוריספטורים. אוקיי, בסדר, אוקיי. אז כאן יש טיפולים כאלה, כדי שיהיה הרבה ממברנה, ועל הממברנה הזו רודופסון. ברוד יש בפנים דיסקיות כאלה, דקות מאוד, רק ממברנה. ועל הממברנה הזאת יש את הרודופסון. האור בעצם בא מפה. It's inverted. אז האור בא מאחורה.
If I want to put this one on the retina, what orientation will it take? Here, let's say here on the eye, you do.
Okay, let me do it again. Okay.
Yeah, let's say this is the eye you do, so how does...
The retina in the back has the photoreceptors in the back, and they send signals to the bipolar, send signals to the ganglion, which send signals to the brain. So it's the outer segment, it's outside, the chutz,
He's getting hit.
the light.
He's getting hit on the leg?
Yes.
So it doesn't get, I don't know, blocked on the way?
That's what I said. It's זה משוגע שזה ככה, אבל זה ככה.
How does it go through?
Because it's transparent. Everything in the body is transparent, except for the pigment epithelium in the back, which absorbs it. Everything else is transparent. Okay? אבל טשטוש יש. And the cones, in the very middle of the eye, there are a lot of these cones, a lot of them, in the fovea. And so many that it needs to push its bipolar cells to the side, and they get connected that way.
And what is the connection to, where is the control on the channels? How do you control
The
opening, closing of channels with
rhodopsin in the membrane affects the transducin, which sends cyclic GMP to the cell, which goes to the channels, which are on the outside membrane.
so this is actually inside the cell?
Yes, in the rod. In the cone, it's on an insole.
Okay. And it happens really fast, because usually these biological metabolic processes take...
No, it's not a metabolic process. It's an enzymatic process. You want to change, changing concentration of cyclic enzyme.
It happens like...
Milliseconds.
So this is a time scale where I can see, like, if I
Yes, sir.
twist very fast, my head is...
Yes.
Kimsel?
Sure, but you need a transducer. It has to interact with the transducer to cause the cyclic JMP, and you need the channels which are sensitive to the cyclic JMP. So you need that whole conglomerate.
So there's a lot of waste of energy in the dark.
Yes.
I mean,
Yes.
it shows that actually when you sleep with high bands, lots more energy than time you're awake. Because leaving these channels open, I mean, doesn't the cell get to zero? Zero
No, it
potential?
keeps pumping.
Pumping is so much better than the flux, I mean,
Yep. Okay, we gotta do color. That's what I figured. Hold on. Okay. I need one for each kid. I need 1, 2, 3, 4, 5. So I need 4 of them. Can you give me? Give me a little more. Good. Okay. Let's go. Let's go. בואו ניכנס. אחד לכל אחד. דף לכל אחד. נתחיל עם בוחן. בוחן קטן. עמוד אחד לכל אחד. מה? בוא נראה. בוחן. אוקיי, מוכנים לבוחן? לא צריכים לרשום את השם, אבל כן חייבים לתת לי את השם. I'm sorry, English, I'm sorry. You don't have to write your names, but you do have to give me in the papers after this, okay?
For what is it?
A short quiz. I figured it's time for a quiz. Okay, ready for the quiz? I want you, without discussing with each other, please. Okay, here are the questions, please. No discussion. Everybody answers themselves. Silence in the room. This is a quiz. Does everybody have a piece of paper? Does somebody have two pieces of paper? Thank you. Who else doesn't have? Everybody has? Okay. These are the questions. Please write the answers very short. Write the answers, and then we'll discuss them. Okay? Okay? Finished? English or Hebrew, you can answer any language you want. French, Chinese. Without discussion. What is what? Crescent Sahar. Yeah. I'm sorry, in Hebrew. Why is the moon sometimes כעיגול, כעיגול ולפעמים כסהר? סהר, נכון? סווט, למה אנחנו מזיעים, נכון? שיבר, למה אנחנו רועדים? רעד קוראים לזה? רועדים מכוח. All done? Okay. Finished? Finished? No? Quickly. Okay. Okay? Let's give a minute, even if you're not finished, so we can discuss. Did I get them all? Okay. Doesn't matter. Okay? Okay, so let's go over the answers. First question. Why is it cold in the winter and hot in the summer? Because we're not in Australia. Very good. Okay, and why in Australia is that's just because it's a different time, but it's also cold there in the winter. Okay. You're right. There it's cold then.
There's an angle between the axis of the rotation of Earth.
Okay. So, number one. Anybody who wrote it's because the Earth is closer to the sun in the summer and further than in the winter forgot all about Australia, because in Australia they have summer and winter in these different times. Therefore, it cannot be the distance of the sun from the Earth. Okay? The orbit of the Earth is indeed elliptical, but it's very, very small difference from a circle. What it matters is the angle of the Earth where we happen to be from the light coming. So in the summer, it's more direct, and therefore the same angle of light hits a smaller area of Earth than in the winter, and therefore we get more heat from the sun in the summer than in the winter. Okay. Why does the moon look sometimes like a disk and sometimes like a crescent? Yeah, yeah? The angle. The Earth hides the sun. Okay. That's the usual answer, that the Earth causes a shadow on the moon. That's not correct. When does the Earth cause a shadow on the moon? In an eclipse, not when we see it. So it's not a matter of a shadow of the Earth. It's a matter of which half of the moon we're seeing. The moon is lit by the sun, and if we're here, and the sun is here and the moon is here, then we see the fully lit thing. When it's here, then we only see half of it lit. When it's here, we see less than half of it lit. So we only see, it's a matter of which part of the moon we're seeing. Okay. Next question. Why do we have two eyes? Huh? Why do we have two eyes?
Two eyes versus one is the benefit in terms of binocular vision.
Binocular vision. Okay. What else? What? Two distinct shapes. So the eye should be two distinct shapes. So we can distinct. Okay. If any of these answers is correct, then the correct answer would be we have two eyes in case something happens to one of them. So we have a second as a spare part. Okay? And about 10% of the population loses vision in one eye during their lifetime. Very often it's cataract, and therefore it's good that they have a second eye as a spare part. Since we have it around, instead of carrying the spare part, the spare tire in the back of the car, we use it in the meantime, and we use it for all the things that you said.
Why not have four then?
We'll get to that in one moment. Why do we sweat when it's hot and shiver when it's cold?
Keep our temperature.
To keep a constant. Why are you taking this course? Okay. So just notice that in the first two questions, you answered why, because. Why is the sun? Why do we have hot and cold? Because the Earth has an angle. Why is the moon? Because of where they're placed relative to each other. The next three questions you answered in order to. Kidei she. You answered, why do we have two eyes? So that we can see disparity. Why do we sweat? So that we should cool off. Why are you taking this course? In order to learn something. Okay? When you answer the question of why you're taking this course, I assume that you are conscious thinking beings, and you thought about whether you should take this course or not, and you decided to take the course in order to learn something. Who did the thinking to decide that we should have two eyes so that we should have stereopsis? Which engineer decided that we should sweat so that we should cool off? Okay? I didn't know that you're all religious and assumed that there's a God who invented and created all this. So, how are you going to save yourselves from this terrible accusation? How are you going to save yourselves? Well, nearly. But it doesn't matter. I haven't read them all yet. It doesn't matter. What is the alternative answer, and what is the interpretation of why you answered it this way? Who's the engineer?
Natural selection.
Natural selection is the engineer. Evolution is the engineer. So evolution made changes in a random way, and those mechanisms which remained because they had a positive effect, because they have an evolutionary advantage. So when we ask why we have two eyes, what we're really asking is, when evolution attempted and tried out one eye and two eyes and four eyes and 10 eyes, why did human beings remain with the two eyes rather than remaining with the alternatives? It seems that there's an advantage. What is the advantage of two eyes over one eye? Stereopsis. What is the advantage of two eyes over one? In case something happens to one, we have a spare one. Okay? Okay? That's what we mean when we say why. When we say, why do we sweat? Because evolution tried out a mechanism. It's called the autonomous nervous system. And the autonomic nervous system makes us shiver when it's cold and sweat when it's hot, and that results in a cooling and heating. Yes, go ahead.
Do you assume that evolution has stopped?
Why did I say that? Why?
Might be just some mediocre interim solution.
Might be. We might evolve still and have much better brains in the future. Yeah.
But I mean, your answers could have been completely different if we had 4 arms and legs and 7 eyes. I mean, you would always have the same answer differently.
That's right. In other words, if we want to think about it, as you asked, why do we have 2 eyes instead of 4? Okay? And then we have to start talking about the cost effectiveness of having 2 or 4. It is certainly very, very disadvantageous that something can happen behind my back and I don't know it. So why don't I have another eye there? Okay? But maybe the cost in terms of brain power, already the 2 eyes are using half our brain. So 3 might use 3/4 of our brain. That might not be worthwhile. I don't know. I'm not pretending that I know all the answers. I'm just saying that when we've talked many times already in the last hour about why things happen and how come and so on, we have to remember what we mean when we say why. Okay? It's shorthand for what is the evolutionary advantage. Okay? That's all I wanted to point out. Okay? And so, I mean, we could have answered, why do we sweat? Because there's a temperature sensor. It goes to the autonomous nervous system. That makes the sweat glands produce sweat. That would have been an answer like we answered this. What's the mechanism that goes to it? Okay. Let's talk a bit about color vision. Why do we see color? Okay. So first question. The electromagnetic spectrum is huge. How come we chose this part of it for vision? I don't know what's wrong with gamma rays and what's wrong with seeing TV.
Cheaper to pick up in terms of the systems involved?
Yeah, it's possible. The truth is that most of the radiation that comes from the sun, even though it is through the spectrum, most of it gets curtailed, first of all, by the atmosphere, okay, and second of all, by our biological cornea and lenses, and therefore most of the energy that comes to us from the sun comes in this range. Okay. So there's a evolutionary correspondence between the nature and the biology. And by the way, rhodopsin is specially attuned for this range. And it's been famously said that if somebody came from Mars, he would also have the same rhodopsin. Because nature only invented one rhodopsin, not every animal having a different one. There's slightly changes in the opsin, and therefore in the exact spectrum. But basically, it's the same. Okay, number one. Number two, a bit of history. Isaac Newton. That's how long ago? 400 years ago, something like that. What he did was take a prism and split light into its component colors. Okay. Then he took a second prism and he took the components and made it back into white. That's really magic. Okay. What that showed was, first of all, color. This thing is red, not because there's something in it which changes the light to red. Light is red when it hits it already. But it's also other colors, and the other colors get absorbed, and the red gets reflected. Okay? So it's not that this creates red. Light does not change its color when it hits something. Hitting something selects which light is reflected and which absorbed. Okay? So that's the first principle that Newton was able to understand. Okay? He also had a problem. How come we give these 7 beautiful names to colors while it's actually a continuum? And it's drawn here with separate colors, but it's not so. It's really a continuum of wavelength. If it's a continuum of wavelength, how come we give it different names? He didn't have an answer. Okay, we go another 100 years. We come to Thomas Young. Thomas Young did everything, but also he happened to have been sent the Rosetta Stone. Have you all seen the Rosetta Stone? Yeah, okay. And in the Rosetta Stone, he was able to do the first step of deciphering the Rosetta Stone because he noticed that some of the words are in cartouches and they are names of people and they corresponded in the Greek to the names, and therefore he was able to say those are letters which have sounds associated with them and so on. But that's not the important thing for us. What's important for us was that he said there probably are 3 basic colors, and those 3 basic colors reflect 3 basic mechanisms in the eye. How did he know? He didn't. That's what he assumed. Because the Greeks already had talked about 3 basic colors. Newton had said, well, all colors are the same. But he said, no, there are 3, and that's why we give them names. Okay. Next came Helmholtz. Helmholtz agreed with his 3 colors, but he went on and did experiments with Maxwell, and he did the following experiment. He said, let's take any color, and let's take one projector of one color, and let's change the intensity until the 2 are the same. Can you do it? Let's say this is yellow and this is purple. Can you make the yellow the same as the purple by changing the intensity? No, it didn't work. Okay. So, okay, let's take 2 lights, one yellow and one green. And now let's try and create purple. Can we do it? No. Okay, let's take 3 lights. And we'll see if we can create any other light with those 3. Will it work? And he found, yes, it works. Okay? Now, let's say the 3 were red, orange, and green. And this was blue. Can you create it? No. So what did he mean by saying that you always can with 3? He allowed you to have a negative intensity light. You could take one of those lights and make it negative. Now, how do you make a negative light? It's very simple. You shine it here on top of the blue. So therefore, if you can take one of them and shine it here, that's like subtracting it from there, and then those 2 and these 2 become equal. Got it? Yes, I know. I'm talking about light. I'm talking about light. No, I'm talking about light. So let's try it again. Let's say you want to equate red, orange, and green to make blue. Can you do it? No. You all know you need the 3 basic colors. Well, there's no such thing as basic colors. But they basically said what any 3 colors are basic colors. But you have to be able to use a negative intensity of light. then you can get it. So let's take the red and add it to the blue. And then maybe it'll be equal to the orange and the green. Yeah.
Excuse me, it's maybe a stupid question. Are you now talking about perception or about wavelength?
Perception
So the reason for this is something that happens in the brain, or the reason is something
in the
that
brain.
happens in the physics?
In the brain, not in the physics. Okay? We all agreed that was Newton. Newton said you cannot change the wavelength of light. A red light is a red light is a red light. If you combine it with other wavelengths, you get white. But it's not because you've changed the wavelength. You can split it up and combine it. It makes no difference. Okay? A wavelength is a wavelength is a wavelength. You cannot change the color of light. Okay? And when this is red, not because it changes the wavelength of the light that hits it, but because it absorbs some and reflects others. Okay? So that's what they said. You need three. And that's why they came up with trichromacy. And they said there are three types of cones. This is the rods. These are the three cones. And they absorb in slightly different places. Of course, they didn't know this. Who knows this? This was found by George Wald last century, 300 years later. Okay, what did he have to do to prove this? First of all, he had to do the spectroscopy. He had to see what light is absorbed by a retina. And then he had to take individual cones and rods and do microspectroscopy to find the absorption of each one. Okay? Good. He also found that vitamin A is involved in retina, in rhodopsin, and so on. Great guy. Okay. So now my question to you is, why three? Why do we need three? And in order to answer the question, I got to draw another graph. Okay. So let's start with one. Oh, I got it with me. Let's say we had only one photoreceptor type, like rods. Why can't rods see color? After all, this is the rod spectrum. So I can tell the difference between green light and red light by the response. Are you with me? Okay. Why can't the rod see color? After all, there's a different response to green as to red.
Green light uses the same signal as bright red.
Very good. Because if we make a dim green light, if we make a dim light, then we reduce everything, and then we get something like this. This is for dim, and this is for bright. And it cannot differentiate between a red light and a dim green light. Is that clear? Okay. So we need something which has two mechanisms. One to tell us about intensity, and one to tell us about... So, let's take a blue receptor and a red receptor. And we'll have two receptors. One gives a big response in blue, one gives a big response in red. And now all we have to do is take the sum and the difference. The sum tells us the intensity, and the difference tells us the wavelength. Okay? We've solved the problem of intensity. So two are enough. What's the use of having a third type of cone?
Better differentiation and through the color means that more inside.
Better differentiation. Not good enough. Because I'm talking about principle, not just a little bit better, a little bit worse. We don't have a third mechanism taking up 1/3 of the retina just to get a little bit better differentiation. What's missing?
Perhaps a problem because a single cone has a bell shape.
All right, I know. What can I do? So you want me to draw them as bell-shaped. So I'll make this bell-shaped, and I'll make this bell-shaped. Okay, now it's better. So it's bell-shaped. I'm talking about in principle. So, in principle, why do we need 3? What's missing here? There's something essential that's missing. Combination of different lights. Okay. So let's talk about combinations of different lights. What combinations do you know? Give me an example of a combination. Purple is one combination. Very good. That's going to be one example. The second example we've mentioned about 100 times already today. What other combination is there? White light. White light is the combination of all the wavelengths. Equal amount of all the wavelengths. If this dual mechanism sees white light, what does it report? The two mechanisms are struck equally. That's exactly the same as this wavelength. This green wavelength is equal to white. Okay? Then we don't have white. Now, maybe white is not important. But if white is important, this isn't good enough. And what she introduced was purple. What is purple? Blue and red. If we combine blue and red, what do we get? A green. Okay. So we can know the wavelength if there's a single wavelength of signal. But if there's a multiple signal, we can't know anything about it. Okay. So we need a third one to add to it. Okay? So now we can get white, because white is all 3, and no single wavelength can do the same as everything together. Yeah.
What if we had 4?
What if we had 4? We would be better. There would be colors that we would not confuse when we had 4, which we do confuse when we have 3. It depends where it is. Do any people have 4? And the answer is yes. In the following way. One of the types of color blindness is that the red pigment is slightly shifted. And it's shifted usually closer to the green, and therefore it's somewhere here, and therefore it's more difficult to differentiate between red and green. Okay? Now, children of parents, one of whom has this wrong position and one has the correct position, sometimes have both. So they have 4 types. And there are confusions which we make that they don't make. Okay? So can we maybe evolve further to have better eyesight? Maybe. Okay. Let's go back. Yeah.
So if we get 4 instead of 3, will there be a qualitative difference or just another more differentiation of the colors?
A qualitative difference. There are some things which will be camouflaged for us and will not be camouflaged for the person with 4.
And this is the same, not the same one, but the same type of qualitative difference between 2 and 3?
Yes. Okay. So, if we have 1, we have no color. We confuse color and intensity. If we have 2, we have the full color spectrum but no combination. If we have 3, we have white and other unsaturated colors and purple, red and blue. Other unsaturated colors, by which I mean the following. When you add white to red, what do you get? Pink. So pink is one wavelength plus all the wavelengths together. If you add blue to white, what do you get? Cyan. Cyan, yes. Light blue, pale blue. Some languages have a word for it and some don't. English doesn't. Hebrew does. Russian does. No Russians here? No. Okay. I don't know about Chinese. Okay. Okay. Would 4 be better? Yes. Okay. Along came Herring, and Herring said, "Lo zubim v'lo yad." Not right. There aren't 3. There are 4. There are 4 mechanisms, not 3. And I'm going to prove it to you, says Herring. Helmholtz, Young, Maxwell said, "What do you mean? We just proved that there are 3." He said, "Yes, you did your experiment. I'll do my experiment. I'll prove to you that there are 4. And here's the experiment that he did. He said, "Look at this. Now, you're all supposed to stare exactly at this cross. Don't move your eyes. Just look at the cross." I'm supposed to have a gray thing afterwards, which I don't have. How am I going to do this? Well, you keep staring. We'll go back to the herring. It's good enough. Ready? You remember, blue on the left top, green on the top right. Now, what do you see? You see colors? Yes? And which colors do you see? Top right is what color? Cyan, red, yeah. And bottom right? Bluish. Okay. So you get the opponent colors. And Herring said there are 4 mechanisms: red, green, yellow, and blue. And they have opponent colors. Red and green are opponent, blue and yellow are opponent. And yellow is nowhere in the 3 trichromacy of Helmholtz. There were only red, blue, and green. He says, there's yellow. What about yellow? And furthermore, he says, we can have a reddish yellow, like orange, but we can never have a reddish green. There are opponent colors. When you mix the 2 lights together, you get white. If you mix blue and yellow, you get white. If you mix the paints, I know you get green. But that's subtraction, not addition. When you add them, you get white. So there are 4 basic colors, not 3. Nothing wrong with his proof. He's right. So if he's right and they're right, what do we have, 3 or 4? Okay? Now, I've already told you that George Wall found, 100 years later, that there are 3 types of cones. So therefore, Helmholtz must be right. But what about Herring? The Herring's also right in the following way. We indeed have short, medium, and long wavelength receptors. 3 types of cones. And when we add up the responses of all of them together, we see brightness, white. And when we subtract them, we get black. Okay? That's how we get strong and weak intensity, by the 3 mechanisms adding together. But we can also take the long and the medium and subtract them from each other. And when there's a stronger signal from the long, we call it red. And when there's a stronger signal from the green, from the medium, we call it green. Okay? So there's an opponency between red and green. And halfway in between is white or black. Because it's 0 when we subtract them. The next thing the brain does is to add together the long and the medium. That's called yellow. Because what the brain does next is to subtract this signal from the blue. And when the yellow is greater, when the sum of the middle and the long is greater than the short, we call it yellow. And when the short intensity is greater than the sum of the red and the green, we call it blue. So how many colors are there? 1, 2, 3, 4. Or 1, 2, 3, 4, 5, 6. 6 is divisible by 3. So there are 3 opponencies. Intensity or darkness, red versus green, and yellow versus blue. Okay? That's how we see. So they're both right. If we take the mechanism, which is red minus green, then at long wavelengths, the red is stronger. Here they're equal. Here the green is stronger. And strangely enough, the red is stronger at the very, very short wavelength. A minor point. The blue versus the sum of the two. Here's the crossover. Now, a strange thing happens at this crossover point. At the crossover point, here between the red and the green, this mechanism, red-green, is inactive. The only thing that's active is the blue. So that's pure blue. That wavelength is the only wavelength that's pure blue. Here, we have the red and the green equal. We have pure yellow. Their sum is not 0. Their difference is 0. And over here, the blue and the yellow are equal, so we get pure green. So we can get pure blue, pure green, and pure yellow. What about pure red? Never exists. Because there's no point where the blue-yellow cross where there's red. It's stronger than the green. And yet, far out here, maybe the red is greater than the yellow. Okay? You can think of it, I now turn the picture on its side, as a dial. And the dial tells us, do we have stronger blue or stronger yellow? Stronger red or stronger green? Two dials. And the third dial being the intensity. Okay? So there's the pure blue where red and green are equal. Above it we have purple, red plus blue. Below it we get blue-green, turquoise. Then we get pure green because the blue-yellow are equal. Now the yellow gets bigger, so we have yellow-green, that's chartreuse. Then we get red equal to green, pure yellow. And above it, yellow, red, orange. Okay? One more thing I wanted to add. These two colors. I assume that this is orange and this is brown. Difficult to really draw. But anyway, I tried. The difference between orange and brown is what's around it. Bright color is orange. Dark is brown. It seems darker because it's got a bright background, and here because it's got a dark background. And they do look different, don't they? But they're really the same. Okay? Okay. We have a few more minutes. So in a few more minutes, I want to introduce the concept of receptive fields, which you've already heard about. Okay? And we'll talk about it a lot next week. And we'll talk about it in the retina, and we'll talk about it in the visual cortex, V1, in primary visual cortex. Let's get the definition that you've already heard from Adi for receptive field. Go ahead. See, when you take notes on the thing, it's not as good as when you listen. Yeah.
The area in the let's say a paper that you're looking at compared to the direction of your pupil. Like it'll be in a certain area within. If I'm looking at a certain way, if my pupil is centered.
I'm looking there. Yeah. Now what?
So your pupil is centered, let's say.
Yeah.
So the receptive field will be in a certain area compared to where your pupil is looking at.
Anybody agree?
So, what are you asking about the receptive field of one neuron, or?
Usually when we talk about receptive field, we talk about receptive field of one neuron. Yes.
Okay.
So what's the receptive field of one neuron?
Then you have to say in which stimulus space you are looking, right? You could speak about the color receptive field or the spatial receptive field of one visual neuron.
Good.
Depends
So,
on your stimulus.
all right. So,
If you are talking about the spatial receptive field of a visual neuron, then it's the area of the retina in which changes of the stimulus change the memory potential of firing back.
okay, very good. great. Okay. So we start with Hartline. Hartline got the Nobel Prize for great work about together with walls and so on. Wait, I want to show you much. But Hartline worked on the limulus. The limulus has what's called a compound eye. We have a simple eye. This has a compound eye. You know the difference? Compound eye has many little eyes. It's got about 1,000 little eyes. Each one has a lens, and each one has not one with photoreceptor. Actually, it's got 7, but it acts as one unit, those 7. They see one part of the world. So what's the receptive field of one ocellus? Is the point out here which it can see. Okay? So he defined receptive field. And then he said, well, what about a secondary neuron which receives information from that one? What is its receptive field? It combines, it's got convergence of information from various ocelli, and therefore it's got a bigger receptive field. Okay? Are you guys with me? Yeah? This is an amazing animal, the limulus. It's got 7 eyes. Just these are the 2 there. There's another 2 here. There's one underneath, etc. Okay, it's a relic from prehistoric times. Okay, you find it only on the eastern coast of continents. You know, in Woods Hole, Massachusetts, in Florida, in Japan, but not in Europe, and not in not in California. Why? Who knows? Anyway, okay, I'll tell you the story about Hartline. Hartline spent a summer at Woods Hole. Woods Hole is on Cape Cod. Cape Cod is an island which sticks out of Massachusetts into the Atlantic Ocean. So it's a great place for doing marine biology because you're right in the middle of the ocean. The other place where marine biology was done was Plymouth in England, which also sticks out into the Atlantic Ocean. So the boats go out and they catch the animal. Hartline goes to Woods Hole for the summer, and he goes to the fishing fleet and he says, every day I want you to bring me a different animal. And every day he took that animal and he tested the vision of that animal. And he happened to like the limulus. So the next summer he said, I want every day bring me limulus. And what you do is you take a saw and you saw the very hard shell here, and you take out the eye, and you very carefully dissect all the tissue around the optic nerve, and then you cut it, and you take the eye, you put it into some salt water, and it can stay there for about 12 hours, and you take the optic nerve and you put it on a hook, and you record what's happening, the responses to spikes. And you shine a light, and you can find out a lot about how vision works. So he liked that very much, but he said, I'd like to record from one fiber, because I want to see the receptive field of one cell. So he took that optic nerve and he dissected it out to try